Hi, my name is Beverly Owens, section M03 with Lab 5 Motion of Falling Objects. We are observing a volleyball and a piece of toilet paper being dropped from rest. The main result is the models gave a good prediction of the observed motion using Newton's second law and knowing force of gravity and drag. We first begin with the toilet paper video, selecting the point of mass at the center and selecting the calibration stick to 0.1143 meters. This is the length of the toilet paper. The video clip begins when the toilet paper is at rest, t equals 0, and ends before the toilet paper hits the ground at t equals 0.633 seconds. Position begins at negative 0.129 meters and ends at negative 0.791 meters. These are the coordinates on the y-axis because only the y-axis is being affected. This is also then done for the volleyball, point of mass at the center, and the calibration stick to 0.207 meters. The video clip also begins at rest at t equals 0 and ends before the volleyball hits the ground at t equals 0.633 seconds. Position begins at negative 0.111 meters and ends at negative 0.981 meters. In both videos, the positive x-axis is to the right and the positive y-axis is pointing up. The initial conditions for the toilet paper and volleyball are set. This is first done by setting the mass of the toilet paper to 0.002 kilograms and the mass of the volleyball to 0.26 kilograms. The initial positions for both were found from the tracker and finding the position when time is equal to 0 for both. The initial velocity for both toilet paper and volleyball were equal to 0 because there were no change in speed or direction. Delta T was set for both at 0.03 seconds. This is due to the time frame being 1/30th of a second. Because only having force of gravity for our model being our only force was not a good representation, we also added a force of drag. This was then changed our F net to F grav plus F drag for both our volleyball and toilet paper models. F drag was equal to our proportionality constant B times speed. Speed is found for each object by dividing the change in position over the change of time. This is a speed of 1.05 meters per second for the toilet paper and 1.37 meters per second for our volleyball. Our B was then found to try to find an ending time in the model the same as the ending time in the experiment when t is less than 0.633 seconds. This allowed our B for our volleyball to be 1.06 and our B for our toilet paper to be 0.0126. Our F grav is still going to be applied as the mass of the object times negative g, which negative g is defined as negative 9.81. Our arrow scale for toilet paper is about 50, and our arrow scale for the volleyball is about 0.5. Here we have our graphs of our toilet paper on the left and our volleyball on the right. The blue line represents our experiment, the red only gravity being in effect, and green both drag and gravity being in effect. We disregarded the gravity models because this did not make a good prediction of what our experiment was. When the graph of the drag and gravity model is graphed, this shows a much better representation of our experiment. The green line represented by our added drag in the model predicts a better motion of our falling object. This is due to the model beginning and ending in the same locations as our experiment. Even though there is a slight variability in the middle, there is still a good prediction of how our object will move. For our what-if question, if the object was thrown initially downward, this would change the initial velocity to some value other than 0. This change would make the graph represent a graph that looks more like terminal velocity than my previous graph of drag. This could be due to the idea of the piece of toilet paper being dropped from a higher distance and having time to reach terminal velocity. So what does this mean? Terminal velocity is not reached in my slow model, which is my toilet paper model. The green line indicating the effects of gravity and drag does show a better relationship to terminal velocity than the gravity line, which is my red line. But because my toilet paper was not dropped from a high enough position, it wasn't able to reach this terminal velocity, which is a velocity of 0.